Hello again everyone, and welcome to the recording for the week 22 GV300 lecture, where we're going to carry on from where we left off last week by continuing to look at multiple regression. So the first thing we're going to talk about is a notion of controlling in multiple regression, and sort of in particular we're going to be looking at, say, the effect that the gender that we were looking at with our dummy variable at the end of last week's lecture, the effect that gender has upon someone's earning income for our fictitious data set that we're looking at. So we're going to be returning to our model A plus B1x1 plus B3x3 as our predictors. We'll remember that we did have a B2x2 and it was age, but for this particular model we're not counting age because we only wanted to have two variables in there to make some of the calculations a little bit easier to do by hand. And so remember that B1 is measuring the impact of x1 on y independent of any influences from x3. So let's have another look at our data. So recall that our data looked as follows. We had people's income here, their years in education here, and we've got gender here, and we can see that we've got our two females are at the lower end of the table here versus income. So we're going to sort of see what impact this has when we actually try and produce our model and visualize our model. So we can look at the original model, and our original model is supposed to be this line down the middle here where y hat is minus 8.84 plus 1.06 xi, and I can similarly calculate a regression line where I look at just the females, and I can calculate a regression line where I look at just the males as well, and my b value for my original line was 1.06, and I'm claiming that if I look at just the females is 0.08, and for just the males it's 1.12, sorry, or it's 1.2. So we're going to have a quick look at where those figures have come from. So if we wanted to work out the relationship between income and education where we were controlling for gender, then let's start by concentrating on the women in the sample. Since there are only two of them, it's pretty easy to calculate a best fit line through 2 points. Is the line which is the unique line which goes through those 2 points. I can work out the gradient very easily just by looking at the change in the y direction divided by the change in the x direction. If I look at the two female people and see that their x values were 10 and 15, their y values were 6 and 2, so this is just reading them off the table, I get 0.8 coming out as my solution there. So that tells me that the slope for the regression line for women in this case is slightly less than the slope for the entire sample of both men and women. The slope for men can't be determined quite as easily as there's 3 men and 2 women, so unless the points were collinear I can't just put a perfect line through them, but I can go ahead and do the calculations for a least squares regression line, and if we were to go back and run through them it would come out as follows, and the key thing here is I'm going to have my 1.15 or 1.2 rounded as I'd written on the previous slide, doing things, or 2 slides back, doing things just to 1 decimal place. So that gives me sort of two values, a slope for men and a slope for women, and if I want to take the average of these slopes as an approximation for what's going on if I'm ignoring gender, then I'm going to get 1.15 plus 0.8 divided by 2, so I'm going to get a value just under 1, 0.98 coming out as my slope. So this is my slope when I'm controlling for gender, and it's a little bit less than the original value that I had of 1.06 when I just had no information about gender at all. So what that's telling me is that when someone's gender is held constant, education has a slightly smaller impact on income in comparison to the situation where the gender is just completely ignored. So this tells me that part of the relationship between education and income is definitely coming from a person's gender. So let's sort of examine it again. We can see that my bivariate model was minus 8.84 plus 1.06 times x1. And for my multiple regression, my multivariate model, I've got y hat is equal to minus 7.37 plus 0.98 x1 plus, sorry, minus 0.88 x3. So I can see that the coefficient associated with, and there is an x3 missing here, sorry, the coefficient associated with x3 implies that females can expect to earn £88 less a week than males. And we can visualize this difference by looking at the following diagram, where we can see that I've got one line for males and I've got another line for females. I can see from my value of 0.98 as my coefficient associated with x1, my gradient or the slope of my lines, that the two lines are parallel with each other. The difference that I'm seeing is down at the intercept, where I can see the difference of £88 a week being reflected as the sort of difference in intercepts between these two lines. So if I've got a dummy variable, this gives me another way of visualizing things. I can visually show the difference between the two groups that I've sort of cut my population or my sample into, so that I can analyze the difference between them. So when x3 is made to equal 0, our multiple regression model is as follows, and when x3 is 1, my multiple regression model is as follows. So I've got two different models out, which was visualized on the last slide, one for males and one for females, and as we said, this implies that there's an intercept shift in response to the change in gender. So we can use the same methods as we've looked at in previous weeks to calculate, say, the R² value, to calculate the goodness of fit, or the adjusted R², and the standardized form of the model, which we did do last week. So we can do those calculations here and see that here I've got an R² of 0.97, which is actually the best out of the three models that I've seen so far, and I can calculate my adjusted R² values as well. And as noted before, if we look at the standardized module, we can see that education has an impact on income nearly 6 times greater than that of gender in response to a sort of a change of one standard deviation. So we've got 0.9 versus 0.15. So we can sort of directly compare things that we wouldn't have been able to compare before, because you can't measure, obviously, one change in years in education versus one change in gender. It just doesn't make sense. So we have to standardize things to be able to talk about these variables in any kind of a comparable way. So the next thing I want to do is just show where our standard errors of estimates are coming from, and we can work out, and I'm not going to justify it, but we can work out a multivariate counterpart to the standard error formulas that we looked at in the bivariate case, and the formula is given here for us all to see. We know that unexplained variance is total variance minus the explained variance as well, so we can use this formula to start working out the things that we need to work out. So we can work out this the sum of the EIs, some of the error terms. So let's have a look at doing that. So the sum of our EI squareds are going to be calculated by the difference between what we observed and what we predicted, and we can calculate that as the sum of what we observed from the mean, subtract the sum of the mean from what we predicted. So if we do those calculations, we get the difference between sort of the total variation and that which we can explain, so the bit that we can't explain. And that's what we're looking for, our unexplained variance here, our unexplained variation. We can similarly work out the other parts of the model that we're interested in, so I can work out the differences between x and x bars and sum them up for my different x bar values, and I can find the other missing parts from the model, which in this case is, say, the R13, so the correlation between R1 and R3, the correlation between x1 and x3, and I can get a goodness of fit value for these points as well. So I can get an R13 squared, and when I've got all this information, I can throw all of this information into the model, or into the equations. I throw all of this into the equations for standard error of beta 1 and for the standard error of beta 2, and I get 0.015 and 0.65 coming out the end, and so that would allow me to, when I'm writing up my model finally, to be able to put the standard error terms in parentheses as well. And again, SPSS will give us standard error terms when we're calculating these regression models. So the next thing for us to consider is what the f-test is like for a multiple regression model. We've looked at this sort of before when we were doing ANOVA tables, and we've looked at the t-tests last week as effectively looking at variables inside a multiple regression model and testing sort of whether one of them has a place there, looking whether the coefficient associated with it should be 0 or should be non-zero. In a multiple regression model, the f-test allows us to do something a little bit different. It lets us test, in a sense, the significance of the entire model, and so it doesn't necessarily tell us what value it doesn't tell us anything about any of the individual variables. What it says is whether there's sort of any strength to the whole model at all. And we do this by looking at the variance ratio, the F ratio, the variance explained by the regression divided by the variance not explained by the regression. And in our model, we've got beta 1 naught equals 0 and beta 1 is equal to 0 for our null hypothesis, and beta 1 is non-equal to 0 for our alternative hypothesis. This is the way things would be if we were doing our t-test that we did last week. So what are we going to be testing now? For a multiple regression model, we're going to be looking at saying beta 1 equals beta 2 equals beta 3 equals beta all the way up to beta k equals 0, or not all of the betas are equal to 0. Beta 1 doesn't equal beta 2, doesn't equal beta 3, doesn't equal beta 4, which doesn't equal 0. So what our null hypothesis is essentially saying that all of the betas in our model, all of the coefficients, should be 0. So there's no strength to our model at all. The alternative hypothesis is that at least some of the betas are not equal to 0, you know, that everything's not equal to 0, and so there is something to our model. There are some things in there that are worth keeping. So as I say, it's a test of the overall model as opposed to the test for an individual variable. As always, we would calculate an analysis of variance table for this. So there's our analysis of variance table, where we'd be looking at the explained versus unexplained variation. And we're going to have sort of the associated degrees of freedoms and the variance calculations with them as well. And it's then up to us to carry out sort of an f-test based upon this. So just a quick word of explanation about the degrees of freedom. Our reasoning for the degrees of freedom in the tables is that, well, if we had one observation, then we wouldn't be able to say anything about variation at all, because we've just got one observation. So in order to say something about variation, we need to have more than one observation. So we've got n-1 useful bits, or n-1 degrees of freedom in calculating the total variance, and if we had 2 bits of information, we could fit a regression line through it, but we'd have no unexplained variance, since our line would be going through the 2 points. They'd be collinear with each other. So we need to have more than 2 bits of information to have any idea about the unexplained variance, and so we've only got we've got n-2 degrees of freedom for the unexplained variance. So total variance minus explained variance is equal to unexplained variance, so n-1 minus n-2 is equal to 1, and so that gives me 1 degree of freedom for my explained variance. So that's where the 1 came from, and the n-1 and the n-2 in the previous table. So going back to our example, we can work out our predicted values of y, and we can work out all the associated differences to be able to do these variance calculations, and we've got everything that we need in the table there to do it. I'll allow you to spend the time to look at the table and look at the look at the table from a page ago or 2 pages ago, and compare with our example here and see if you can fill in all the figures. If you do it correctly, you should get the following. So we should get an ANOVA table that looks as we have here, which leads to an F ratio. We've got a lot of explained variance compared with not very much unexplained variance. We've got an F ratio of 70 coming out, of 60 coming out here, 60.9, and so we need to test that with an appropriate value from the appropriate F distribution. So we need to go ahead and do that. So we'd look up an F table if we needed to. So for example, we'd go to a stats book, or we'd Google it and try and find an F table online. And if we found an F table with 1 degree of freedom in the numerator and 3 in the denominator, which is what we need here, and we looked for the 95 percentile point, or the point that leaves 5% in the right hand tail of the distribution, then we'd find 10.1 is the value that we get, and so 60 is bigger than 10, and so we've definitely got enough evidence to reject H0 and conclude that our model is explaining some of what's going on. Remember, it's not telling me which variables inside the model are strong or weak, it's just telling me that there is some that we can conclude that in this model there are variables that are worth keeping and variables that are worth looking at. So it's quite a handy little test if we just want to be able to see how a model as a whole is behaving without having to worry about all of the individual parts. The last thing that we're going to do to finish off is look at the relationship between T and F. So this is just sort of a mathematical aside to finish the lecture, really. So we're going to say that we've seen from earlier that y hat minus y bar is equal to b times by x minus x bar, and given that that's true, we can sum over the values of y and sum over the associated values of x. What we have is still going to be true. We're still going to have an equality between these two things. We can also recall that the standard deviation in this case is given by this formula here, and we know that in terms of our variance we've got the explained variance divided by the unexplained variance, and we can write that formula as b squared sum of xi minus x bar squared over s squared. And so we can then do some calculations with this because we have a calculation, or we have a value for s at the top of the page. And so if I go through and do this calculation for s, then I can see that, sorry, for f, then I can see that f is equal to b squared over s squared divided by the sum of xi minus x bar squared, and I can play around with the algebra, and again you can sort of check this through yourselves if you feel so inclined, but what we spot at the bottom is that when we've done these calculations we just end up with the square of the t distribution. So we have a relationship between the f and the t that we've been looking at, in that f is just equal to t squared. So you know, it doesn't make the biggest impact for you when you're actually carrying out a calculation, when you're reading the values off of SPSS, but it's nice to be able to look at some of the maths in the background and see that there is a link between these things that we've been playing with. And I think we're going to leave it there for this week, and I'm going to let you go and now have a go at doing the associated SPSS exercises. There's sort of some revision for you to have a go at this week of just some sort of standard linear regression in SPSS, and then there's a multiple regression question as well, a longer multiple regression question. And as always, take the time to write them up properly as though you were writing up a solution in your exam, because I want you to get good at actually sort of writing out proper answers to these, as well as being able to sort of copy and paste the SPSS into your Word document effectively, so that when you're sort of doing the exam, this is something which is second nature to you rather than something that you're struggling against to get done. So please do take the time to have a go at answering these questions in full. And then next week, when I'll be back in class, we'll sort of be able to take the time to go through anything that people have sort of want some extra input in from the 2 weeks that I've been away, and we'll be moving on to the last of our multiple regression lectures as well, along with sort of more exercises and more SPSS work for us to do. So as I say, take the time to do the questions, watch through the video again if it's useful to you, and if you have any problems then please drop me an email, and as always I will be doing my best to check them and to reply to people sort of as quickly as I can. Okay, I'll see you all next week.